Hi everybody, my name is Misha. First of all, I would like to thank the conference organizers for making this great meeting possible. I have learned a lot, and the title of my I have removed the words direct bandgap from the title because I decided to add some results about silicon in the end. So now it reads analysis of the attainable efficiency of beta-voltaic elements. And the reason why I was allowed to give a talk here is because beta-voltaic effect and photovoltaic effects are very similar. In both cases, you have ionizing particles that enter semiconducting material, ionize it, produce electron-hole pairs, which are separated by the built-in voltage, and that electricity is obtained. The difference between beta and photovoltaics is twofold. First, the energy of a photon is usually sufficient to produce only one electron-hole pair, but not more. Very rarely two. A beta particle coming from a radioactive source has the energy of tens kilo electron volts, and so it can produce tens of thousands of electron-hole pairs. Now, it would seem that the higher this energy is, the better, but unfortunately, beta particles, if they reach certain threshold, which is of the order of 300 kilo electron volts, they do radiation damage to the material, and we don't want that. So the most popular sources used so far are tritium, nickel, and promethium. The second difference between beta and photovoltaics is that, well, unfortunately, the typical flux of beta particles is about 1 million times, 100,000 times as weak as the flux of photons coming from the sun, and that means that the net power produced by a beta battery is 3 orders of magnitude weaker than that produced by a solar cell. Anyways, in spite of this, beta elements, beta batteries have several attractive features from the point of view of industrial applications. The first one is that the decay half-time is years or decades, and so a beta battery can work for a very long time without need for recharging. Second, the total energy produced in the course of one service cycle of a beta battery is more than 1,000 times greater than the energy produced by an electrochemical cell. And finally, last but not least, beta batteries are very autonomous. They can be used anywhere. They do not rely on the presence of the sun. So they can be used in hostile or inaccessible environments. They can be used in the outer space or at the bottom of the ocean, and in a wide temperature range. So here are some applications of beta batteries, and this is a very nice review article published by Olsen, Kabaoui, and Elkind. Olsen is one of the pioneers of this business. Now, before discussing the main question of this talk, I would like to say, that is the efficiency, I would like to say a few words about the generation of electron-hole pairs by beta electrons. This is given by the generation rate presented here, and it is an integral over all initial energies d E naught involving the initial distribution of energies, and which is here. It is derivable within the Fermi theory of beta decay. And this is the energy loss function, which was obtained by Hannes Bethe many years ago. So a beta particle enters the material and does the ionization. Here is the ionization potential. Here, these are classical formulas. So once we can plot this generation rate as a function of distance from the surface, and we find that it is not quite exponential, but it is exponential enough in the first 2 orders of magnitude. And by doing these calculations for various source semiconductor combinations, we could find the absorption coefficient alpha, which turns out to increase with as the energy is reduced. And there is another important factor in this business is that it is the presence of the dead layer. It is a thin layer of the order of, well, not very thin, about 1 micron. Near the surface of the material where beta particles produce electron hole pairs much weaker, at a much smaller rate than in the bulk. And we take into account this dead layer by introducing this Heaviside theta function, which is 1 if you're past the dead layer of the thickness xm. So now coming to efficiency. Efficiency, because the power is so small, each percent of the efficiency counts. And efficiency is defined in the standard fashion as the maximum power produced by the element divided by the input power. The standard formula for the efficiency takes care of the fact here that not all beta particles actually reach the semiconductor. So this is the first term. Then some of the betas get reflected from the surface. Those betas that produce electron hole pairs, well, some of the electron hole pairs recombine, so we need to introduce the collection coefficient here. And the last term involves the open circuit voltage, the field factor of the current voltage characteristic, which looks the same as in photovoltaics, divided by the energy to produce 1 electron hole pair. And of course, the numerator involves this, can be expressed in terms of the maximum power produced. So now there is an upper efficiency limit. You cannot do better than that. Carnot line efficiency. It is simply the ratio between the band gap energy, which would be the maximum energy, the average energy that you can extract from one electron hole pair, divided by the energy to produce that electron hole pair. And it turns out that for many materials and for various types of radiations, alpha, beta, gamma, Claude Klein has obtained a semi-empirical formula that this energy to produce 1 electron hole pair by an ionizing particle is about 2.8 times the band gap plus half an electron volt, and it takes into account the fact that when you are promoting an electron from the valence band to the conducting band, initially it is very hot, this electron, and then it drops down to the bottom of the conduction band and produces phonons. About 1.8 Eg goes into acoustic phonons, and about half an electron volt is taken up by the optical phonons. So this theoretical maximum efficiency increases with the band gap and levels off at large band gap materials at about 34%. You cannot do better than that. Anyways, now what we want to do to be more realistic, and we would like to include the effects of recombination, which are not included in this formula. These effects, they sit basically in the collection coefficient and in the open circuit voltage. So we need to find those two quantities. We proceed in a fairly standard manner. So for collection coefficient, we work in the short-circuited regime. We write down the continuity equation in the stationary case. It involves the effects of recombination, which we take into account the Shockley-Reed-Hall recombination and radiative recombination. L is the diffusion length, G of x is the generation function, so this is a standard equation. The boundary conditions, the first one takes into account the fact that the p-n boundary, the electron hole pairs get separated, so the excess charge carrier density is 0 there. And at the back side of the base, we have surface recombination taking place, so this boundary condition, and then this is the collection coefficient, defined as the ratio of the current, diffusive current at the junction depth divided by the total number of electron hole pairs produced by unit time. This equation can be solved. So this is the result for the special case of 0 surface recombination rate. When SD is not 0, then the expression gets a bit longer by about a factor of 3. So anyways, so we have the collection coefficient. We also can get the open circuit voltage, in which case we so the open circuit voltage is found from the standard. Again, the standard expression also used in photovoltaics. Delta P star is the main player in this expression. It is the minority carrier density at the boundary between quasi-neutral and depletion region. So it can be, we assume that the emitter is thin. So this delta P star is found from the balance equation, which equates the generation current to the recombination current. Here we have surface recombination rate and the recombination rate in the space charge region, which the expression is again standard, but it is some nonlinear function of the unknown delta P star. So in the end, this has to be solved numerically, and the open circuit voltage can be found. Coming to some of the results, we compare here the performance of a gallium arsenide. We compare the performance of promethium and tritium as sources of beta particles, and we find this is the efficiency, and we find that tritium outperforms promethium by about a factor of 3 or 4. This is for different Shockley-Reed recombination types. Now this, but still the efficiency is between 4 and 8%, not very high, but it agrees quite well with the experimentally found efficiencies for tritium source for this combination. It can be compared, the maximum efficiency, which I have introduced a couple of slides before, is about 32% for gallium arsenide. And also from our analysis, we can obtain the Shockley-Kayser limit of the efficiency when all the recombination channels are turned off and only the radiative recombination is there. And it turns out that in this limit, the efficiency is about 17%. And I don't know how much time do I have. Yeah, okay, well. And the last slide here is, so we also looked at nickel-silicon combination and found an interesting effect that efficiency can be maximized if you change the thickness of the p-n junction. And the maximum here occurs at about 16 micrometers. The reason for this effect is that the collection coefficient turns out to increase with the thickness, and open circuit voltage drops with the thickness, and so competition between these two effects lead to maximum of efficiency. And coming to the main, maybe the main message of this talk is that it seems that the possibilities to maximize the efficiency of beta voltaic elements are not exhausted yet, and there is a lot of room for improvement. You can play around by choosing the right semiconductor beta source combination, or even by tailoring the geometric parameters of the junction. So with this, I would like to conclude my talk, and thank you for your time.
Thank you very much. Any questions? Okay, please.
Thank you very much for a very nice talk. You go to your efficiency chart as a function of the band gap of the material.
Here.
Right. If you look at that, it seems that if you're operating with silicon at 1.1 eV in that chart on the right, you're at perhaps 28, 29%, is that correct?
Yeah, but it's sort of a Carnot efficiency. It's absolute maximum efficiency which you cannot exceed.
And I grant you that.
Yeah.
But
yeah, that's right. Yeah.
The trend would hold in that if you go to higher band gap materials.
As a matter of fact, it does. Yeah.
Right. So as you go to higher band gap materials, the increase is, shall we say, relatively small. And so my question is, you've shown results for gallium arsenide, but can you comment where silicon stands in this one? So, for example, experimental results in the order of 4 to 8%.
well, silicon is about, the maximum efficiency is about 28%. For gallium arsenide, the maximum efficiency is 32%, which is not a big difference. But their combination mechanisms are different. And that's why silicon outperforms.
So if I might perhaps lead the discussion further, can you comment on the role of the reverse saturation current in
No, I can't.
and the thermal generation?
No, I can't. Sorry.
And in particular, coming back to your original title, what's the role of direct and indirect damping in the context of the
The importance of that part, the initial motivation was the importance of the radiation. The difference between the two types of materials is radiation, which is much more intense in direct damping. So I thought that if we imagine that all other sources of the combination are from both channels of the combination are from both, then we could get this formula for direct band gap materials, which is shortly what I call shortly tracer materials.
I have further questions, comments, but I don't belong.
Okay. Just a couple of questions. Obviously, the vacuum creates electrons there which are not carriers.
Sorry, can you repeat?
The carriers generated by the vacuum are obviously not carriers, much higher than the conductor band or valence band edges. Can you give me a sense of, can you calculate the distribution of energy of these electrons that are generated by the voltage?
We didn't work with it. We are working with the mean, with the first moment of this. But I didn't look at anything.
Just to add that he's right, but after the thing is done, and we are doing different work, I thought here we are doing our after the other work we are using. And one other hypothetical question, not hypothetical, is naturally is but you are analyzing an external vacuum source.
Sorry?
You are analyzing an external vacuum source.
Yes.
An external source of not vacuum of iron electrons. How would an internal source change your calculation?
This is an interesting question that I would like to explore in the future myself. Quickly made the semiconductor a bunch of interesting elementary processes to happen. Region turning to children, flying waves, asymmetric free, and so much. It's complicated, but actually it's the efficiency, the first term of the efficiency, what fraction of beta switches the semiconductor. And the way I knew the picture was that there is a source on top of the junction, so half of the beta fly in the wrong direction. So in reality, people are trying to maximize the fraction, and they sandwich the beta source between two semiconductor parts. In terms of tritium is deuterium. So people are trying to use portable silicon to store tritium in which case the beta battery might be below